All right, get this thing started here. I'm going to log into the same meeting from another account, just so nothing goes awry here. And let me share my screen. All right. Start with that. Let me get this to work. Cool. All right, got my other self in here. Hopefully that keeps the meeting from stopping mid-meeting. All right. Okay, so we're going to go over this final exam review, but I just want to give you a quick rundown of all the sort of circumstances surrounding this last exam. A couple of things to keep in mind. This exam review right now is happening on Monday, the 8th. The exam will be available starting tomorrow on Tuesday, the 9th, all the way through this Saturday. Normally, exams are open all the way till Sunday. Not the case with this one. You need to finish it by Saturday because I need to get all my grading done, probably most of it done on Sunday, because grades are due early the following week. So just be mindful of that this week as you're trying to fit it into your schedule. Um, but you should be able to, kind of again take it. It's the same amount of time, 90 minutes as the previous ones. The real exam is shorter than this practice exam. If you tried the practice exam here and you felt like it was long, it is long. It covers more stuff than is on the real final. But I just kind of wanted to give a big overview of kind of everything that we've talked about this semester, all in one exam. The only other things worth mentioning is make sure you get that final project turned in if you haven't already. They're starting to trickle in. I've got maybe 10 or 15 of them now, but that means there's a lot more of them outstanding from other people that haven't turned them in. So get that turned in as well. It's worth a good chunk of your grade. And I think that's it for the logistics that I wanted to go over. So let's go ahead and dive into this exam review. To do that, let me turn off my video here and fold up my computer. It looks like nice. We got somebody in the actual recording here. Just feel free to pipe up if you have any questions along the way as we go. All right, so when it comes to doing the real exam, it's going to be, again, the same sort of logistics as the previous exams. Log in to Respondus, have your ID, do your environment check, start the exam. The exam will be a little link in that problem that'll open a PDF. There will be access to other links that you can use to use the spreadsheet that's built into Respondus. You can have your calculator. And on this one, you can have a full sheet of notes front and back. So basically 2 sheets of notes relative to the previous ones. I will also include tables A2 and A3 again for this exam, but if you have your own already printed out, that's fine. You can include those. That doesn't count towards your 2-page note limit. So just keep all of that in mind. As usual, I think it's wise to skip the multiple choice and save those for the end. So that's what I'm going to do here. We'll come back to these multiple choice, but I want to start with, here we go, with the big word problems. And I guess one thing I should mention that I didn't yet is that last time, before we did the exam, up in this space above the exam, I did a big decision tree. That decision tree is probably worth having on this exam as well to kind of help you narrow down which type of problem you're dealing with, to distinguish between the chapter 8 stuff, the confidence intervals, and then the chapter 9 and 11 stuff, the hypothesis test. I'd also encourage you to use that table as you work on the final project. You've got a couple of problems on the final project that come from that section, and you can use that table, or that decision tree rather, to help you kind of narrow down which type of problem to look at. So I'm not going to recreate it here because I think that's going to be a waste of time, but go back and watch the recording from the previous exam, exam 3, if you want that, if you didn't get it, or a lot of you I saw included it in your notes. So feel free to include it in your notes again. Okay, let's take a look down here. Problem number 11. So this one says, the number of touchdowns thrown by Tom Brady during the years from 2001 to 2015 are listed below in chronological order. We're asked to find the mean of this data, the median, the mode, the sample standard deviation, give the 5-number summary down here, decide if there's outliers, draw a box plot. So basically all of chapter 3 condensed into a single problem. So let me just write that down. This is really all a big chapter 3 problem that we're working on here. The easiest way to do this problem, in my opinion, is going to be on the calculator. I'll go ahead and show you how to do it in Excel as well in a minute, although I don't think I opened Excel. I'll have to open that in a minute. All right, so hopefully this is, just knocking the rust loose. It's been a while since we've done problems of this particular nature, but these were some of the first ones that we did on the calculator. So the first thing we're going to need to do is enter that data, hit our stat button, and edit a list of data. Right now I have some data from some other problem that we were doing, maybe exam 2 or something like that. I'm going to clear that data out. So again, I can highlight the name of the list, hit the clear button, and hit enter, and it'll erase all the data from that list. As a reminder, if you accidentally hit delete instead and delete the list altogether, you can restore that by hitting the stat button, going down to where it says setup editor, hitting enter again, it'll tell you it's done. And now if I go back to my lists, that list that I just deleted is restored. Okay, so I'm going to put this data into that list. Let me just do it without talking so I don't make any dumb mistakes. And hopefully I can type them all in. All right. Let me just double check. I'll highlight the last one that I entered, that 36. It tells me that's in position 15. That tracks because these were from the years 2001 to 2015, so there should be 15 pieces of data there. It looks like I didn't miss any. Let me just scroll through, make sure I didn't accidentally mistype any really obviously. They look good to me. I don't see any obvious mistakes. So let's go ahead and compute our statistics. We'll hit the stat button, go over to our list of calculations, so go to the right, and just do one var stats. And the only thing that we need to be mindful of is making sure that we are treating this list as the list that we are wanting to apply our statistics function to. So L1, that's where I had it entered. And then I need to make sure I clear out this frequency list. So let me clear that out because each one of these numbers appears exactly one time in the list as I type them. We don't need this frequency list. There are a few examples of problems throughout the semester where we used it, but not this kind. So let's hit calculate, and it's going to give me a bunch of the stuff that I need. First and foremost, it gives me the mean, and that's exactly the first thing listed right here, the X with the bar over it, which has meant sample mean since the beginning of the semester. So to ensure that you can get some partial credit in case you screw up the numbers, I always prefer to write in the formula, or at least a brief description of what that quantity, how that quantity can be found, or what it means. So this would earn me half credit. This is the formula where we add up all the individual values, then we divide by however many values were in that list. And in this case, the number we got for that was about 28 point, I'll just call it 53. It's 28.53. And what are these? These are touchdowns. So make sure I include my units here. Oops. All right. The median also shows up in the list. It's down here. If we scroll down, MED is short for median. So that's the value that we're looking for here. The median is just the middle value. If we were to order our list from smallest to biggest and find the middle of that list, it's another measure of center. similar to the mean, but it's not as, or it's more resistant to things like outliers and skewness. So it can be useful in certain situations, but I'll just write down what it means. So the median or middle value in an ordered list is, and it looks like this is 28 this time. So 28 touchdowns. The mode is not included in the statistics that this gives us. So I'm going to skip ahead to the other ones that are. For example, the standard deviation, the sample standard deviation is included. The sample standard deviation, the formula for that is, or the symbol we use for that is S. And the formula is we sum up the difference between each value in our list and the observed average, the mean. So our X bar value, we square all of those and add them up and then divide by n minus 1 and then take a big old square root of the whole thing to get rid of that square that we did. This gives us the value that we're looking for. In this particular case, we are going to get, scrolling up, this value right here, the S. S refers to the sample standard deviation. Sigma is what we would use if we were dealing with an entire population, all the values. But in this case, it's a sample because these are only some of the years that Tom Brady played. So it's just a sampling of his years. So in this case, we're going to use S. Not only that, but it also tells us to find the sample standard deviation. So S is the appropriate one here. And it's about 11.11 if I round that to 2 decimals. And that also has units of touchdowns. And while we're at it, we'll do the 5-number summary because that is the last 5 numbers that the calculator spits out. The minimum, the first quartile, the median, which is the same as the second quartile, or the 50th percentile right in the middle, the third quartile, and the max. So let me just list those values out. We're going to find the min, the first quartile, the second quartile, which is the same as the median, the third quartile, and the max. Those numbers make up our 5-number summary, and they are respectively 0, 24, 28, 36, and 50. Hopefully that 8 is readable. Will bug me. Let me erase that one. No, that's not much better. Good enough. Okay, and again, these are all touchdowns. So I'll just abbreviate it there. So the one that we weren't able to find on the calculator is the mode. The easiest way to spot it, so the mode is just the most frequent value in the list. So I guess I can write that down. The mode, or most frequent value, or most is the word I'm looking for, most frequent value that shows up in the list. So we can look at the list and just by observation try to figure out which number shows up more frequently than the others, so which one shows up most. But the easiest way to do that on the calculator is to sort those values. So if I hit the stat button and I choose to sort either in ascending order or descending order, you can pick. I'm going to do ascending order, smallest to biggest, and tell it to sort L1 for me. Now when I go back and look at it, all the values that are the same will show up right next to each other. So we had 0, 18, 23, 24, 25, 26. Each of those only showed up one time each. As I scroll, oh, it looks like 28 shows up a bunch. I should see it 1, 2, 3 times. 36 showed up twice. And that's it. Looks like 28 showed up the most. It showed up 3 times. So the number 28 is what we're looking for when it comes to the mode as well. So in this case, that is also 28 touchdowns. And again, you could have observed that 28 simply by counting through this list, but I think sorting it makes it easier to spot. So your mileage may vary. The last thing that we're asked to do is figure out if there's any outliers and then draw a box plot based on that. So the IQR method is the method that we've been using to determine outliers, and it starts by computing the interquartile range. The interquartile range being basically the difference between, the third quartile, come on, pen, third quartile and the first quartile. So it's just the difference between the third quartile and the first quartile. So 75th percentile 25th percentile. This covers the middle 50% of our data, and we want to see how spread out that is. Once we have a good sense of how spread out the middle 50% of our data is, we're going to use that as sort of a ruler or a scale to determine which of the other values are far from the bulk of the data, because that's all an outlier is. An outlier is a piece of data that falls far from the rest of the data, but we need to define what we mean when we say far from the rest of the data. So we're going to use this IQR as sort of a measuring stick. In this case, the values that we got are 36 and 24. I pulled them from right here, my third and first quartile, and that difference is 12. I can do it in my head. You don't need to do it in your head. You can do it on the calculator if you want. 36 minus 24. Okay, so my interquartile range is 12. The formula then to determine our boundaries beyond which we'll consider any data that shows up to be an outlier is the following. We have a formula for the lower outlier boundary and one for the upper outlier boundary, which I will abbreviate LOB and UOB respectively. So the lower outlier boundary, we start towards the bottom of the data, that first quartile, and we're going to measure down 1.5 times that IQR. And that's going to give me a boundary. If any data shows up below that boundary, we'll consider it an outlier. For the upper outlier boundary, we're going to start towards the top of the data. So we'll start at the 75th percentile, the third quartile, and we'll measure up from there, 1.5 times the IQR. And so when we plug into this formula, the lower outlier boundary is going to be Q1, which is 24, minus 1.5 times the 12 that we just found a minute ago. On the graphing calculator, it's nice. It'll do our order of operations. It'll take care of the multiplication before anything else. So we can just do 24 minus 1.5 times 12. And it gives me a lower outlier boundary of 6. Any pieces of data that are smaller than 6, we'll consider that to be an outlier. For the upper outlier boundary, it'll be similar. I'm going to plug in Q3, which is 36, and I'm going to add 1.5 times that 12. And in this case, I get 54. So just be mindful that if you're doing this on a non-graphing calculator, you'll need to do your order of operations. You should start with the 1.5 times the 12 first, get that number. In this case, that's 18. And then you'll come back and do 24 minus 18 to get the lower bound, and then 36 plus 18 to get the upper bound. And there you get the same 6 and 54, but you'll have to kind of break it into steps. So in this case, I want to take a look at my data and decide if I have any outliers. Is any value in this list bigger than 54 or smaller than 6? Well, looking at my 5-number summary, I know my maximum value is 50. So at the highest end, the largest number in our actual data set is not bigger than 54. That means we don't have any outliers. This is not considered an outlier because it's not beyond our boundary of 54. It's not bigger than that. So no outliers at the high end. But at the low end, we have the 0, which is smaller than the 6 here. And that's the year I think he got injured in the first quarter of the first game or something like that. Didn't have any touchdowns. Didn't really play that season. But that makes it an outlier in this particular case. So we have one season where 0 winds up being our only outlier because I can double check by hitting my stat button, going back to my list, and seeing that the next smallest number in my list is 18. And 18 would not be considered an outlier. It's bigger than this 16. So the 0 is the only outlier that we've got in our list. And so that's what I will write. 0 is the only outlier. And we'll use that to draw our box plot. So our box plot should always start with a number line. So just a big, long horizontal line. And it needs to span basically the whole range of values that we're interested in. So 0 at the low end, we got to get up to at least 50. So I'm going to count by 10s. We'll call it 10, 20, 30, 40, 50. I'll go all the way up to 60, in fact, just so I have a little extra room. And notice that I tried to space these lines as evenly as I could, just at least by as well as I could eyeball them. It doesn't have to be perfect. And now we draw, so these are our touchdowns. There's my label. The box portion of the box plot spans the entire interquartile range, so it needs to cover this region. In fact, if I go up to, let's try to get it all on the screen at once here. If I go up to here, it spans from Q1 up to Q3, so it needs to go from 24 up to 36. So 24, if I had to eyeball it, I would say 24 is right about there. 36 is going to be right about there. I'm just, again, eyeballing it. Those are going to be the ends of my box. So let me draw in my box. There's the box portion of my box plot. Within that, we put another dividing line at the second quartile or median. So that's going to be right around here-ish, a little bit to the left of that 30. And I'm just going to label them. There's Q1, Q2, and Q3. That's how I decided where to put the left, middle, and right ends of this box. From here, we have the little whiskers that stick out and go to the minimum and maximum values that aren't outliers. And at the high end, we have our outlier boundary being at 54. So we have an upper outlier boundary over here. It means that in this case, I can extend my whisker all the way to the highest value at 50 and not have to worry about dealing with any outliers because the maximum value is 50. It's not beyond this upper outlier boundary. So basically the idea is that these little lines, these whiskers, cannot cross these imaginary boundaries. At the other end, that was at 6. So my lower outlier boundary is right about, oops, didn't mean to do that. Right about here. There's my lower outlier boundary. And in this case, if I tried to extend the line all the way down to the smallest value here at 0, it would cross that line. So that's not allowed. What we have to do instead is go down to the smallest value that's not an outlier. And looking at my list of values over here, the next second smallest value of my list is 18. So that's all we're going to do. We're just going to go down to the 18, which would be right about there. So this is the minimum value that's not an outlier. And that's where we need to go. The actual outlier over here is going to be marked with an X. So this is the real min in this case, but it's an outlier. We mark outliers with an X. We would do the same approach if there had been an outlier on the high end. We'd mark it with an X, and this line would simply go up to the second smallest or largest value, basically the largest non-outlier value. And you can have multiple outliers, and they would be marked with multiple X's. So just be mindful of that as you put this together. None of these labels that I did here with the upper outlier boundary, the lower outlier boundary, or the min, or the max, or the quartiles, none of that is necessary. I'm simply putting them in place so that as you look at this and try to study on your own, you understand why I chose to put this whisker stopping here, and this one stopping here, and the box stopping from here to here. So just keep all of that in mind. So hopefully this is a good quick refresher. I'm going to show you, for those of you that don't have a calculator, I want to just run through a bunch of these same quick calculations using Excel, but I need to open Excel. Let me open a, come on, computer, don't freeze. Oh boy. All right, no, there it goes. Just a momentary pause. Come on. I should have opened this beforehand. Come on. If I can find it this way. Is it really not going to like that? There's Excel. Don't freeze, don't freeze. All right. So if you're taking this approach, on the exams, I try to provide that data already to begin with. So let me just type it in real quickly. Hopefully I don't make any mistakes with my typing here, but you would already start off with a little spreadsheet with the data that looks like the following. That looks good. There are my 15 pieces of data. These would all be the touchdowns. Let me make this a little bit bigger so it's easier to see. In fact, I'm going to come borrow some space just so it's easier to see. Okay. let me just write, in fact, let's do it this way. You write in each of the things that we're going to want to find. We're going to want to find the mean, the median, the mode. So I'm just labeling things. We're going to want to find the quartiles and the standard deviation. Um, and was that all? Mean, median, mode, standard deviation, quartiles. We've got min and max. I think that covers everything that we needed to take a look at. Okay, so let's see what the formulas are for each of these. If we want to find the mean, we start with our equal sign. In our spreadsheet, you always start with an equal sign when you're wanting to apply a formula. And you can start typing one of the words. In this case, the word is not mean, the word is average. So I say I want to compute the average, open a parentheses, and then you can just click and drag, to tell it which ones you want to include in that calculation. You can also type those in. And sure enough, there's that 28.53, the same thing that we found on the calculator. For the median, it's equal sign median. I can type. Ooh, there we go. And again, you can either click and drag to tell it which data you want included, or you can also simply type A1 would be this cell here down to A15. And I'll do that on this one. The nice thing is Excel does give you the mode. Oops, I forgot my equal sign. So equal sign mode has different versions that'll either give you multiple modes. If there are multiple, it'll convert it to a single mode. Even if there are multiple, we can use the version of this down here that's just mode. And again, I will just type in A1 colon A15, and you'll automatically see it highlight those cells over here, hit enter, and it gives us the same 28 that we found doing it by hand previously. For the standard deviation, we do our equal sign and we start typing standard deviation, ST, and you can see a couple already. These are the two we're looking for. There's stdev.s and stdev.p. So that's standard dev. Dot S would be for the sample, dot P would be for a population. But in this case, we're looking for the sample standard deviation, so I'm going to do the dot S version. Again, do my parentheses, click and drag or type those values in, hit enter, and sure enough, there's that 11.11 that we found on the calculator. And for the quartiles, it's equal sign and then the word quartile. And we want to feed it not only all of the data, but we also have to tell it which quartile we want to find. So if I'm looking for Q1, I will do comma 1 to tell me that I'm interested in the first quartile. And it'll give me a slightly different number than we found doing it on the calculator, and that's because Excel uses a slightly different calculation. What does it mean to be a quarter of the way through this list of data? Well, there's only 15 terms, so a quarter of the way should be somewhere like in this ballpark, bigger than 3, less than 4, and that's exactly kind of what it did. It found a weird kind of value in between these if I had them sorted. They aren't sorted here, but that doesn't matter. So it tries to find something kind of in between two values. Okay, the next one, same thing, equals quartile. This one we know is the same as the median, so it should give us the 28 that we already found, but let's just double check that. And now I would do 2 for the second quartile. Sure enough, it gives me 28. And one last one, too tiny, there we go. Equal sign quartile, feed it the data, comma 3, hit enter, and it gives us 35. So I just want to point out the two numbers that we found for the quartiles on the calculator were 24 and 36. Using Excel, they're 24.5 and 35 because they do a slightly different calculation. That would mean that these numbers would be slightly different. Both would be counted as correct when I grade this, regardless of which approach you've taken. I will ensure that you get full credit if you used Excel and or full credit if you used the calculator. But it will also impact this next step here at this stage. If I use these two numbers for my first and third quartile, my interquartile range isn't going to be 12 anymore because now it's going to be 35 minus 24 and a half. I'll only get 10 and a half, 10.5 for this value. And it's going to change my lower and upper outlier boundaries a little bit, and it can potentially change the question of whether or not we have an outlier. I don't think it does in this case. I don't think it does, but it potentially could. But again, on the real exam, whichever of the two approaches you take, both will be counted as correct. Okay. Let me minimize that, bring this back, and let's take a quick look. Before I move on to the next question, do you have any questions? No, there's only, I think it's just one person in here. If not, then let's just keep on boogieing through. Stop me if you do have a question or if you want to come back to anything. Okay. Now, here's one where I meant to correct this typo. The age of a tree and that should say height of a tree. The age of a tree and the age of a tree are definitely correlated. I wanted age and height. Cool. So question number 12 here and question 13, both of these relate to the most recent stuff that we've covered in class since the last exam. We just have that one chapter, chapter 4, that talks about correlation. It's really cool stuff. It's an interesting chapter, but it's kind of separate and removed from the other stuff that we've been doing in the class. So I want to make sure we spend some time on this because this is really our only chance to review those topics. So correlation has to do with the nature of the relationship between two separate variables. And it might be possible that there's no relationship between them. But it boils down to two types of correlation. We have positive correlation and negative correlation. Positive correlation refers to relationships where the variables move together. So as one increases, we expect the other variable to also increase. Or as one decreases, we expect the other variable to also decrease. So when they have the same behavior, that is positive correlation. If they move up together and move down together, that's positive correlation. If they move in opposite directions, that's negative correlation. So as one variable increases, the other one decreases. That's an example, or that is the situation we would be seeing if we're dealing with negative correlation. So as we go through this list, we have 4 different scenarios. We've got to determine whether the correlation between these listed variables is positive, negative, or neither if there's no obvious relationship. Let's take a look at the first one, the age of the tree and the height of the tree. And there can always be, exceptions to the rule, but we're talking in generalities here. In general, as a tree gets older, as its age increases, what happens to the height of that tree? Well, it tends to grow as it ages, and so the height increases as well. So as age goes up, height also goes up. And so because these two variables are moving in the same manner, they're going up together, this would be an example of positive correlation. B, we have the horsepower of a car and the fuel economy of a car in miles per gallon. So as the power in a car goes up, what happens to the fuel economy, how much fuel it uses? Again, we're talking in generalities here. We've got to think about, excluding or finding ways to deal with electric vehicles and all of the sort of different things that you could find sort of little obscure exceptions to the rule. But in general, the more power a car puts out, the more fuel that it uses. So as the horsepower goes up, the amount of fuel used goes up, but the amount of fuel is not exactly what we're asking for here. We're asking for miles per gallon. So fuel economy is kind of the opposite of the way the fuel is used. In this case, if the horsepower goes up, a car with 1,000 horsepower, you're not going to expect that car to have very good miles per gallon, maybe 5 miles per gallon or something like that. Whereas if the car doesn't have very much power, maybe you can get 40 or 50 miles per gallon. So as the horsepower goes up, the fuel economy actually goes down in this case, because that's the way that we're measuring the fuel usage. So this one goes up, this one goes down, they move opposite of one another. This would be an example of negative correlation. For part C, we're talking about the amount of time spent running on a treadmill and the number of calories burned. So the longer you spend on a treadmill, so the more time, the amount of time goes up. The number of calories burned also should go up. They move together. This would be an example of positive correlation. And then this last one, the height of an adult person and the number of pets that they own. I don't see any relation between those two things. Generally speaking, right? there's no reason to expect any sort of connection. So this would be an example where I would expect to see no correlation between these two variables. So that's kind of what we're looking for here. Conceptually, that's kind of the most important takeaway. And this is, again, chapter 4. So just write that down. Where's my pen? There we go. Chapter 4. Really, in this case, 4.1. For number 13, we're going to continue on this idea. We're going to delve a little bit deeper, but this is also chapter 4, moving into section 4.2. So we're going to do a little bit more detail, not just the big picture concept, but sort of the nitty-gritty of looking at an actual example. So this one says, consider the concept of correlation for a two-variable data set. Specifically, consider the following table showing the poverty rates, which are measured as a percentage of the total population that lives in poverty in a number of states, and then the college attainment rate in those same states, so measured as a percentage of residents holding a bachelor's degree in those same states. All right, so in the first list here, we have the poverty rate. It tells us what percentage of the population lives in poverty. And over here, we have the college degree attainment, what percentage of the population has a 4-year degree. Big picture, this is kind of similar to the previous ones. Are we expecting positive, negative, or no correlation? Well, generally speaking, fewer people, or essentially the more people that live in poverty, the less likely they are to be able to afford to go to college. So as poverty rates increase, you tend to see college attainment decrease. Alternatively, you could, that's sort of implying one causes the other, but the other approach could be equally true, right? Maybe it's the lack of college degrees that leads to poverty. It's kind of a chicken and egg type question. We don't really know which one causes the other. It's probably a cyclical relationship, but that's not important when it comes to correlation. All we care about is there a relationship and what is the nature of it? So in this case, I would expect as poverty rate increases, I would expect college attainment to decrease, or similarly, as college attainment increases, I would expect to see less poverty rate go down. So as one goes up, the other goes down, and vice versa. That means I think we're dealing with negative correlation in this case. And that tells me in a minute when we find the correlation, the equation for the least squares regression line, and when we find the correlation coefficient should be negative, and the slope of my least squares regression line should also be negative when we get to that part. So let's take a look here. I want to compute the correlation coefficient as the next step in this process. The correlation coefficient is the statistic we computed that uses a lowercase r as the symbol for the correlation coefficient. It has a big ugly formula. It looks like basically a 1 over n minus 1 times the sum of the product of two big z-scores. So we take the z-scores of every single value in our list x, we multiply those by the corresponding z-score of every value in the list y. We sum up those products, and then we divide by n minus 1. So this winds up being an average of the product of those z-scores, basically. And this was the example that we did way, I guess, last week, whenever we watched this, where if you have a scatter plot that's kind of broken up, if most of the dots in your scatter plot, after we put in our sort of our axes here, our bullseyes, where this would be our x bar value and this would be our y bar on our axes. So if we have something that looks like this, if most of your stuff falls sort of up and to the right and down and to the left, clearly there's a positive trend line here. And those are both situations where either both the x and y values are above average, and hence both have positive z-scores. We multiply them together and get a positive value. Or they're both below average, so they're both negative, and we multiply two negative numbers together and get a positive. So if most of your stuff falls in this one and this one, those give you positive contributions to your correlation coefficient. Whereas if most of your stuff falls in this little section or this section, this is where one is above average, the other is below average. And same thing up here, one is above, one is below. So in that case, one z-score would be positive, one would be negative, and this product would be negative overall. And we get a bunch of negative contributions and wind up with a negative correlation coefficient. So in this case, I'm expecting a negative correlation. I'm expecting a picture where most of the stuff would actually fall over here and over here. And we can even maybe do a little quick scatter plot. Maybe it's worth doing that here. I didn't ask for it as part of the problem, but let's do it real quick. Let's just see what that might look like. What would a scatter plot look like for this particular problem? So down here tells us in a minute, tells us that we're going to use poverty rate for X, college attainment for Y. So this is going to be my X's. This is going to be my Y's. So we have poverty down here. We have college over here. And the poverty rate spans from the lowest value is 11. The biggest value is 19. So maybe just call it like 10-ish here. Go 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. I'm writing in all these numbers. Maybe that's unnecessary. Let me zoom in a little bit. Maybe we want to count by twos because it's going to get messy if I try to include them all. So maybe we'll just do the even values here as we write 18, 20, and so on. And then those are the poverty rates as a percentage, and then college attainment. The low I see here is 22 all the way up to 38. So maybe I only want to count by fives over here. Maybe we'll start at 20 as the low end. Then we have 25, and then 30, and then 35, and then 40. So pick a way to count that you make sure that you can cover the entire span of values here. And I want to just put in a dot corresponding to each one of these pieces of data. So for Connecticut, for example, their poverty rate is 11, so they're going to be somewhere above this little hash mark. Their college attainment was 38, so they're really up high. Let's call it right around there-ish. Colorado is at 12 and 38, so that's going to be just a little bit further to the right, but the same height up. That looks like more than one dot. Fix that first dot. So there's two dots sitting next to each other up there. Next one, Florida. Poverty rate is 17. College attainment is 27. So 17 is over here. 27 is quite a bit lower. 27 is going to be down here. Nevada, 15 and 23. So 15 is right here. 23 is pretty low right here-ish. Utah is down at 12 and 31. So 12 up to 31. That's right here, I guess. Ballpark. And what else? Kentucky, 19 and 22. So 19 for the poverty rate. That's way over here. 22, that's the lowest number yet. So that's going to be like down here. And sure enough, you can kind of see that there's definitely a downward trend. If I had to try to fit a line to this, I would say my line is doing something like that. It's going downward. So I'm expecting that negative correlation coefficient. Let's see what we actually get when we do this on the calculator and get the actual value. And I'll again show you how to do that. Sorry, I just need to get some stuff out of the way here on the screen. There we go. I'll show you how to do this on the calculator, and then I'll also show you how to do this in Excel in just a minute. Come on, don't freeze. All right. It's not liking this. Come on. Oh, this trusty old computer. Let's see. There we go. Just had to fold it out. Woke it up. Okay. Let's find this correlation coefficient. So on the calculator, turn it on. I'm going to enter my data in this case, so I don't have to erase the old data. I'm going to just do it in L2 and L3. And let me zoom up so I can actually see all the data. So in L2, I'm going to put my X values. So I'm just going to type those ones in, 11, 12, 17, 15, 12, and 19. Got those values in. Let me just highlight it. Looks like I've got 6 of them. Sure enough, I've got 6 of them. Looks like I didn't miss any. And now I'll do this list. 38, 38, 27, 23, 31, and 22. And they all match up. They look exactly like what I've got here. Just make sure you don't sort either of these lists because that'll break the pairing. Right now, I want to make sure that that 11 goes with that 38 and this 17 goes with this 27 and so on. And if you were to sort one of these, it would break that pairing. So now that I have this, what we need to do is compute our correlation coefficient. To do that, this was the thing where we had to turn this functionality on in the calculator. So let me go through that one more time here. We need to turn on diagnostics, otherwise it won't print the value that we're looking for out. In fact, let me just show you what it looks like when it doesn't print it out. So I'm going to hit my stat button. I'm going to go over to my calculations, and you can select either option 4, this linear regression ax plus b, or in my case 8. I'm going to stick to 8 because that's what I did in the previous videos. That's what the book says to do. So I'm going to select that option 8. And now we just need to tell it which list to use for x and which list to use for y. Right now, this one is wrong because I did mine in L2, L2 and L3. So we need to change that one to L2. L3, that one is fine. Leave my frequency list blank and hit calculate. And what it gives me, oh, I guess I've already got mine turned on. So my diagnostics are turned on. Let me turn them off so you can see what it would look like if you don't actually have them turned on. So to do that, I'm going to go into my catalog, go to the letter D, go to the diagnostics. The default is diagnostics are turned off. Okay, so if you haven't done this step yet, your calculator will look like the following. Let me redo that. So I hit the stat button, go to calculations. I'm going to select option 8, pick the right value or right list for x and y, hit calculate. And it just gives you the equation of the least squares regression line, which is useful. We're going to need that in this next part. Notice we've already got that listed out here. So y bar equals negative 1.903x. And that's exactly what I need here. The one that multiplies x would be b, and b is that negative 1.903-ish. So that one lines up with that one. And then the a term here has no x associated with it, so it must play the role of this 57, right? This is the one that has the x right there. This one does not have the x. So a is the one that does not have the x. It must be this 57 number. Sure enough, lines up with what we've got there. So without turning on diagnostics, you can get this part, but it doesn't give us the correlation coefficient. So to force it to give us the correlation coefficient, it uses that calculation, it computes R in the course of giving us the A and the B. It just doesn't print it to the screen for us to see. So by turning on diagnostics, it's going to compute those background calculations and display them for us. So again, the way to do that, I did it real quickly a minute ago. I want to go into the catalog, which is the second option of the 0 button. So hit second, 0. And this gives you a list of basically every function in the whole calculator. I want to go to the ones starting with the letter D. So I'm going to hit this button down here associated with the letter D to kind of skip down a bit, and then just scroll until I see the one I'm looking for, diagnostic on. Hit enter again, it'll tell me done. It's turned that diagnostics on. And now when I do those same calculations we just did a minute ago, it will spit out not just the A and the B, but also this R squared and R. R squared, that's related to section 5.3, which is one of the extra credit assignments that you can do. And R is the one that we're looking for right here, though. So this number right here, R, oops, let's not do it in red. Oh no, everything's wonky. Hold on. It's letting my, okay, this is, come on. Oh no, all right. Let's try this again. Let's make this tiny. Let's make it big. Let me undo the last few things that I've done. Okay. You guys cannot see the issue that I'm having, but somehow my screen became uncalibrated, and now where I'm touching on the screen where I'm trying to write is like half an inch away from where the line shows up. Let me see if I can get this to just stop doing that. Why is it not making it full screen? What's happening here? Don't want to annotate. Let me stop sharing and then reshare for a minute, see if that has any effect. Stop my share. There we go. All right, give me a minute. Come on, record. Oh, all right. Let me close it and reopen it. Let's try this. My apologies. All right, let's try this again. Always with the technical difficulties. Let's see if it's fixed. Let me just check if that got fixed or not. All right, seems to be fixed. All right. Let me share again. All right. Back to my Zoom controls. Let me share my screen. Okay, got it working again. Boy, oh boy. All right, here we go. So, correlation coefficient is that number that we just found on the calculator. I'll show you again momentarily how to find that in Excel if you need to use the spreadsheet to find it. But it is this negative 0.861 approximately. Oh, let's go back to my controls here. Come on. You have 0.861. And the fact that it's negative makes sense because I was expecting negative correlation in this situation. So that should always match. The sign of your correlation coefficient should match the type of correlation you're expecting. So don't accidentally leave off the minus sign if you have a minus sign. It's easy to kind of miss the little minus sign sitting right there. Okay. Next question. Now that we have this correlation coefficient, it seems to match the intuition that we've got so far. We are asked to use the least squares regression line, which is given here. So it's predetermined for us. We're asked to use that to basically predict the college attainment levels in New Mexico, where the poverty rate is 21%. So in this case, what we want to do is plug in the poverty rate. Remember, the poverty rates were the x values. So I'm going to use this equation, but I'm going to plug in for x. And what I'm going to do is plug something in right here, the New Mexico value, their version of x, and see what we get out of this. So what is the appropriate value to plug in? Well, in this case, I need to plug in the same number in the same format as these numbers here. So because it's 21%, I'm not going to plug in 0.21, right? 21% would be 21 out of 100. That'd be the decimal 0.21. What I'm going to instead do is just do the number 21. And the reason for that is because that's exactly the format that these numbers were entered in. So if I take a look at the way that we entered our data in order to even get the equation of this line, they were all entered just as whole numbers. 11% was just entered as 11. 12% was entered as 12, and so on. So make sure that the format that you enter this number matches the format of these numbers in this list. And when we do that, we are going to get negative 1.903 times 21 plus 57.104. And hit enter. And we get about, in this case, 17.14. And that's a percent. That is our college attainment. It's saying that based on the data that we have available, if we followed this trend line all the way down to the state where in New Mexico, right, poverty is 21%. The highest number we had here was 19. So 21 is over here. It would be right there, this little hash mark, that would be 21. I'd have to kind of follow it down, and this is the value that it would be predicting based on following the red trend line. So this would be New Mexico down here. That's the prediction it's getting. And you can see that it's kind of off the chart downward. We would need to extend this line downward. This was counting by 5s, 20. This would be maybe 15. And sure enough, that looks like it's going to be a little bit more than the 15. So 17 kind of makes sense if you imagine this axis also counting downward from there. So that's what it's predicting, at least, about 17%. Are there any limitations to this? Well, the answer is yes. There are always limitations to using this type of approach, this least squares regression approach. And in particular, one of the biggest limitations is doing what we did here, where we extrapolated beyond the data that we have. What this means is, what I know looking at this picture is that I have data from right here to right here. This is the region where I have some sense of data, some sense of what's going on. It's kind of in this realm. From the smallest value up to the largest value of my x, the furthest left to the furthest right, I went from about 11 up to about 19. And I know that in this region, the data kind of follows a general trend line, and this looks like that general trend line. But after that, we don't have any data, so I don't actually know. Maybe the dots over here would start to level off, and they would go more like this, and I would expect it to switch from being a straight line to maybe it curves and levels off. The point is, we don't know what's happening over in this region. I don't know if it continues to follow a straight line. Maybe it dips down and goes even further straight down. Same thing to the left. I don't know what it looks like below this 11 point, 10, 9, 8, what it looks like further to the left. This could level off flat this way. It could spike upward. It could keep following the straight trend line. We just don't know. So the point is, I really only know what's going on in the yellow region. And if I try to make guesses outside of that region, so it'd be totally viable to say, maybe in a state where the poverty rate is 14%, we could get a good guess that it would give us about 30 for our college attainment rate. But over here, New Mexico was outside of the yellow area. It fell too far to the right, outside of the region where we had data. It felt over in this mystery region. And so I don't know if this is a good guess, because I really don't know if this trend line continues going in that direction, or if it flattens like this, and maybe this is a terrible guess. So that's the idea. In this case, the big issue that we have is there is a limitation. We are extrapolating. And this is a no-no. We are not supposed to extrapolate. We are extrapolating beyond the region where we have data available. And sometimes it works, especially if you're not going too far outside the region, but it's never guaranteed to work. So there's limitations. The point is, we're using this to make guesses. The whole point of these least squares regression lines, the point of regression is to be able to make guesses and fill in incomplete data. But we only have a high level of confidence that it's going to do a decent job of that in the yellow region. And once you move outside of the yellow region, now, we can still say we think this is a good guess, but we don't really know that for a fact. We're just guessing at that point. So just be mindful of that. Okay, I think we've beat this one to death. Any questions about this one? Really, this whole page, the chapter 4 stuff, the new stuff. If not, then let's keep going. Let's take a look here. Number 14. Let me zoom in a bit. Okay. This one says, a basketball player has a career free throw percent. Oh, you know what? I lied. Let me go back before we move on. While I'm still thinking of it, let me do the problem that we just did in Excel. So let me make this a little bit bigger so I have more room. I think this is the last one that we really need to use Excel for. Let's take a look. All right, I'll go back up to the last problem. We did it all in the calculator. It was great. It was nice. It was easy. But let's see if we can reproduce, for example, this correlation coefficient in Excel. To do that, let me zoom down go down a bit and let me put this data in. So 11, 12, 17, 15, 12 again, 19. So those are my x values. These are the x's. Here are my y values. They are 38, 38, 27, 23, 31, and 22. Okay, if I want the correlation coefficient down here, we just said that that is r. We do equal sign and start typing correlation. And by the time I get a few letters in, it gives us a hint and tells us that this function here, correl, will return the correlation coefficient between those two data sets. So all I need to do is do my parentheses and give it the two lists. Give it list 1, comma, list 2. And then close my parentheses, hit enter, and sure enough, what does it give me? It gives me the exact same number that we found on the calculator, this negative 0.861-ish. So that is the command in Excel. It's equal sign correl for correlation. If I wanted it to give me the least squares regression line, the calculator gave me the least squares regression line. In this case, it didn't matter because I gave it to you. But how would we find the least squares regression line if I wanted that? I'll abbreviate it, least squares regression line. Just review how to do this. Hopefully my Excel does this okay, but it is a weird function because it returns more than one value, and they're always a little bit weird. So let me start with my equal sign. And the command in Excel to do a least squares regression line is linear estimate, because we want to estimate our data with a straight line. So it's linest is the command, linest. And it, again, will ask us for the two lists of data, but it'll be very specific. It wants the y's first. Last time I did the x first when I highlighted stuff, but it says the known y values. That's these values. So it wants those first, then my comma. Now it wants the known x values. And then it has these two other things, constant and stats. Those are sort of extra things. It should work without them. Let me just hit equals, enter, and it gives me the two values right here. Here is my slope and my y-intercept, the values that we found here and here. This does not always work if you have an older or different version of Excel, and this functionality doesn't work great in the spreadsheet that's built into the lockdown browser. So on the real exam, I'm not going to make you calculate this directly. In order to pick the appropriate one that you're looking for, I'm going to make it a multiple choice thing, and you can reason through, for example, right? Should my line have a negative slope or a positive slope? Should my y-intercept be positive or negative? And you can use those kind of visual cues and geometric cues related to the equation of the line to guess which one is appropriate. You're welcome to use the calculator or try this to get the value, but there's no guarantees. They're constantly making updates and trying to fix the spreadsheet in the lockdown browser. But this is the one that, at least as of a year ago, I think was the last time I checked, this functionality wasn't working in the lockdown browser, or I couldn't get it to work the first try at least. So again, maybe this is redundant. It's probably not going to affect a ton of people, but just know that is the command that you can use, this linest, but it may or may not work in the spreadsheet in the lockdown browser. If it does not work for you, you should still be able to figure out what the appropriate equation of the line is, because I'm going to make it multiple choice, and you can just use the slope and y-intercept to kind of decide whether those are positive or negative to decide what it should look like. Hopefully that makes some sense. Okay, now we'll be done with that problem and move to question 14. Okay. This one says, a basketball player has a career free throw percentage of 78%. In a given game, he shoots 9 free throws. We want to determine the probability that he makes a given number of those free throws. So let X represent the number of made free throws. This is a binomial distribution. Just to remind you, it's been a while since we talked about them, but this was chapter 6, in particular 6.2. So this was section 6.2. Chapter 6, section 2. I'll just write it 6.2. We can tell it's a binomial distribution, A, because we used shooting free throws as like one of the examples when we first did this. But second, because binomial distributions show up whenever you're repeating a simple yes, no, make, miss, success, failure situation, like the one we've got going here, shooting a free throw, make or miss, success or failure, whenever you're repeating that multiple times. that's a good hint that you're probably dealing with a binomial distribution. In this case, we're repeating that experiment of shooting a free throw 9 times. And we have a percentage that gives us the probability of success for every single one of the times that this person shoots a free throw. So this is a binomial distribution. We're going to do this on the calculator. Excuse me. We'll also do it. I'll show you how to the command in the spreadsheet as well to do this type of a problem, and we'll go from there. But let me just lift this back. Sorry, I got to keep going between typing mode and handwriting mode. So go back. Okay, so this is a binomial distribution. Let me just write that down. There's no points for that given on this problem, but maybe there will be on the final if I do one like this. But just keep that in mind. That's what we're looking for here. So in this case, we're interested in the probability the player makes exactly 7 out of the 9 shots. The formula for the probability of event X occurring, X successes, looks like the following. It looks like NCX, where this is that combination function that we talked about way back when, P to the X, 1 minus P to the N minus X, where N, P, and X are respectively, this is the number of trials, this is the probability of success, and this one is the value that we're interested in. So in our case, what are each of these values? Well, there are 9 total trials because we're shooting 9 free throws. The probability of success for a given free throw is 78%, so that number is 0.78. And the value that we're interested in this case, X is 7. We want to know the probability that they make 7 of their shots. So this is the formula that we would use. In practice, though, the calculator functionality that we use is the binomial distribution. There's 2 of them. There's binom PDF and binom CDF. So we're interested in the probability that X is equal to a given value, that X is equal to 7. This means whenever we have a situation like this, we're going to use binom PDF. And let me show you where to find those on the calculator. On the calculator, let me clear this. They're under this distributions button. So we hit second vars to get to our list of distributions. And the distribution in this case is our binomial distribution. So scroll down until you see that. PDF is if we're interested in one specific value. If I was interested in the combination of all the values up to and including a given value, this is when I would use binom CDF as a reminder. So we want PDF in this case because we're interested in the probability that they make exactly 7 out of the 9 shots. So the number of successes is equal to 7. If it said we want the probability a player will make 7 or fewer of the shots, then we'd want binom CDF. So what is the value in this case? We're going to select that top option, plug in N, P, and X in that order, and hit paste in this case. If you have an older calculator that doesn't take you to that menu, this is just how you would type it in. It'd be binom PDF, and you do N, comma, P, comma, X in that order, hit enter, and it gives us the probability that we're looking for, 0.306-ish. So about a 31% chance that they make 7 out of the 9 shots. In this case, it then asks for what the expected value is. How many shots do we expect this person to make? Well, the formula for the expected value, which can be given by either of these 2 notations, just to remind you, this is the values that we talked about previously, the expected value of X or the average of our random variable X. The formula is very simple. It's simply N times P, and this formula only works for binomial distributions. There's a more complicated formula in the generic case. So in this case, N is the number of trials. It's the 9. And P is the probability of success. It's 0.78. So I just need to multiply those 2 numbers together. Basically, I expect them to make 78% of the 9 shots. And that's all we have to compute. What's 78% of 9? Turns out it's a little over 7. 7.02 shots. Don't round this number. Give me the decimals. The decimals are important. We don't just say, oh, that's 7 shots. We say 7.02. Even though it's not possible to make 7.02 shots, it is possible to make 7.02 shots on average. Maybe one time they make exactly 7. The next time maybe they make 8. Then maybe they only make 6, and then they make 7 again. And if you repeat this experiment over and over and over and over, it should average out to 7.02 shots out of the 9. That's 78% of the 9 shots. That's how many I expect them to make. If I'd wanted to find the standard deviation, it didn't ask for it, but if it had asked for a standard deviation, the formula for that looks like this one. And in the binomial distribution, it's pretty straightforward. It's n times p times 1 minus p, and then we take the square root of that. So we could have found that as well. The standard deviation, this would have been 9 times 0.78 times 1 minus 0.78, and then we take the square root of that whole mess to get the answer that we were looking for. So I'm not going to bother to do that one. It didn't ask for it, but that's certainly a feasible thing. Both of these formulas only are relevant in the case that we're dealing with a binomial distribution. If you're dealing with a general discrete probability distribution, the formulas are a little bit uglier in general. So for our generic cases, the expected value, the formula is this. We multiply x times p of x and then sum those up. And our standard deviation looks even uglier. It's the sum of x squared times p of x. And then we subtract off whatever we just found for the expected value, subtract off that quantity squared, and then take the square root of this whole big mess. So those are the generic formulas. We did these ones, for example, on the problem. We did a problem in class that was like expected winnings or losings from playing the game of roulette. On the exam 2 that covered this material, I think we did like a lottery ticket problem, and these were the appropriate formulas to use for the lottery ticket problem. These formulas over here only work when we're dealing with binomial distributions. These formulas work in generality for any one of these probability distributions, any discrete probability distribution. Okay. Let me just pause again real quickly. Any questions at this point? We're still doing good. I'm going to keep on going. Looks like question 15 here is a confidence interval problem. And I can tell that. So this would be an appropriate place to go use that decision tree that I talked about. We don't have it here because I didn't want to spend the time in redoing it. But if you'd had it from the last exam, from that last exam review, this would be a useful one to, oh, you know what? And I screwed up. Well, I'm going to do this one anyways, but I accidentally included a problem. This was one of the extra credit sections. So this one is actually from section 8.3, which is extra credit. This is not fair game for the exam. I got to change this next time I give this practice exam out because I totally forgot. So we just changed which sections were mandatory. This is the first semester where this has been an optional section, and I totally spaced that out when I was writing this practice exam. So this is an extra credit section, and it has to do with the word proportion here, the fact that we're doing a confidence interval for the proportion as opposed to a mean. Instead of doing this, let me just make up a new problem on the spot here. Let's see if I can think of something. Oh, I have a good one over here that I was looking at earlier. Let me see if I can bring one up. Let me get it up on my other computer, and I'll see if I can replace this one. So just be mindful, this type of problem is not fair game for the exam. This was one of the extra credit sections. It will not show up in this form on the exam. Okay, let me do two things because I have another problem. I just need to go run and grab it. I had one that I was looking at earlier that I was thinking of putting on the real exam that I wound up changing and switching it up. So I can find that in a minute, but I also forgot to do this one in Excel. So let me do that real quick while I'm thinking of it because I always forget about the people using Excel here. Okay, how do you do these binomial distribution problems in Excel? in Excel, we can compute areas associated with normal distributions or similarly, these binomial distributions. All we need to do is start with an equal sign and start typing in the name of the distribution that we want to use. So in this one, it's a binomial distribution. By the time I type in binom, I see this binom.dist. That's the one I want to use, binom.dist. And it will ask for the same three values that we did on the calculator, but in a different order. It'll ask for the number of successes. So this is what we think of as our X value. In this case, that number is 7. So it's asking for the number of successes that we're interested in computing, 7. How many trials total were there? 9. And what's the probability of success? That is our 0.78. So we're entering the same three numbers, these three numbers that we entered on the calculator, but in a different order. On the calculator, we did N, P, X. Here we're doing X, N, P. X, N, P. And then the last thing it'll ask for is, do we want to treat it like a cumulative distribution or not? So basically, this is the distinction between the binom PDF and CDF. So if we do want it to be cumulative, that's the CDF. I would put true if I want to treat it like a CDF. But because I want it to be treated like a PDF, I would put false in this case. And hit enter, and it'll give me the same 0.306 that we found on the calculator. So I just wanted to point that out. And then similarly, these calculations, just to show you that you can do this, you can use any calculator, but you can also use Excel for these calculations. Again, as long as you start with an equal sign. If I want to simply do 9 times 0.78, I can do equal sign 9 times 0.78. And for the times, I'm just using the little star. So shift and the number 8, or if you have like a number pad, the star for multiplication. Hit enter, and it gives me that same 7.02. So we can do these problems here, the binomial distribution, in Excel as well. All of them we can do in Excel. Okay, let me pause for just a minute as we were moving to this one. I saw that somebody else just joined us. We are about to be working on problem number 15 from the practice exam, but the problem is when I wrote this, I forgot that we had just made section 8.3 one of the optional sections, extra credit. So it's not fair game for me to test on it, but this is a problem from the extra credit section. So I need to go find a replacement question real quick, and then I need to give myself a little note to rewrite this before the next time I teach this class. So this is basically no good. That's what I'm trying to get at. That's not a good question because it's a section 8.3 question. So let me run and grab, I had a problem a minute ago that I was working on a different example that I thought was pretty good. So let me go see if I can find that real quick. Just give me like 1 minute here. I'll be right back. Okay, I got it. What's going to be the easiest way? Do I handwrite this? Can I try to copy and paste it? See if I can just copy and paste this little piece in here. I don't think that's going to work, but maybe. All right, hold on just a second. Let me see if I can copy and paste this. All right, no, not that one. Just snip just that piece of it. Almost there. Apologies. Let's see. Control V. Did that work? Kind of worked. Made it way enormous. Okay. Look at that. I'll cover that up there. All right. Let me share my screen so you can see what I'm talking about. And we'll get going. Okay. Just copied and pasted and hid the old question, put a new one on top of it. Okay. So let's take a look at this. All right. So this one says, excuse me, boxes of cereal are labeled as containing 14 ounces. In a simple random sample of 34 boxes, they're observed to contain an average of 14.21 ounces with a standard deviation of 0.18 ounces. We want to construct a 99% confidence interval for the mean weight of the boxes. So in this case, this one is no longer an 8.3. This one, we've got to decide, is it 8.1 or 8.2? And the fundamental distinction between them always boils down to whenever we're talking about the standard deviation, is it the standard deviation of the entire population of all boxes of cereal, or is it just the standard deviation of the boxes in our particular sample? So if we read the second sentence, this is where it gives us the information we're looking for. In a simple random sample, in fact, let me just move this so will that let me move? No. All right, we're going to leave it be. In a simple random sample of 34 boxes, they are observed to contain an average of 14.21 ounces with a standard deviation of 0.18 ounces. So here's that standard deviation, 0.18 ounces. Is that referring back to just these 34 boxes, or is it referring to all boxes of cereal? Well, based on this sentence, it looks like we're just talking, both of these statistics are referring just to the 34 boxes in our sample. So this number, this 0.18, is S. It is a sample standard deviation. And that means this is a section 8.2 problem instead of a section 8.1. If it instead said boxes of cereal are labeled as containing 14 ounces, the standard deviation in the weights of all boxes of cereal is 0.18 ounces. And then it says in a simple random sample of 34 boxes, they have an average of 14.21 ounces, period. In that case, if the 0.18 was referring to just boxes of cereal in general, in that case, it would be our sigma value. It wouldn't be S, it would be the population standard deviation sigma, and this would make it an 8.1 problem instead. So this is a chapter, sorry, my Zoom controls are covering my whiteboard controls. There we go. Chapter 8.2, or section 8.2 problem. Any questions on that? Because that's really the trickiest part of these, is distinguishing Is this 8.1? Is this 8.2? Is
I
this
don't. I think I'm good.
okay? You're feeling okay about that? I really
Yeah,
would go back and practice. If you have any doubts, that's the one thing to kind of go back and practice. The good news is it won't like if you accidentally treated this like an 8.1 problem, you definitely lose some points, but you could still get, two-thirds of the points on this problem, even if you kind of took the wrong approach.
and
So
for the exam, all options of that like T or that tree are all fair game, correct?
yeah, we don't, luckily
Okay.
there's not too many. It was just what, six? So two types of confidence intervals, 8.1 or 8.2. And then there were four different types of um, hypothesis tests, the
Okay.
9.2, 9.3, 11.1, 11.2. All four of those
Beautiful.
are fair game.
Okay.
So just because we did 8.2 here doesn't necessarily mean you'll get an 8.2 on the real exam. The real exam could be an 8.1. No guarantees one way or the other. And then
Okay.
similarly, when we get to the hypothesis test, whatever one we do here, it might not be that exact same type. So it's probably worth your while to maybe try to go back and try like one of each type if you can find a good example.
Okay.
Okay, well, let's knock this out. These aren't too bad. They don't take too much trouble. Part A is always on these ones. It's the same as our step one of our 5-step process. Give the point estimate. This is just our best guess. If we had to try to guess the average weight of the box of cereal, of all boxes of cereal, we would guess 14.21 based on the data that we have available. In our observation, we observed an average of 14.21. That was only for those 34 boxes, not all boxes. But if I'm trying to predict the average weight of all boxes, then using my sample as my prediction for the population is the best I can do. And again, this really fundamentally ties into one of the main ideas from this class. Why do we even care about samples? What's the point of a sample? The point of a sample is we only care about it in as much as it is a good representation of the population. And because the population is too hard to study in its entirety, we take a sample and we hope that our sample is a good reflection of the population itself. And that's really the point of what we're doing in this problem is we're taking a sample and saying, I think it's good. I know it's probably not exactly correct, but it's going to be close. Let's give it a little buffer. And now I can be pretty confident that somewhere in this little, plus or minus margin of error, the true value, the value that I actually care about, the value of the weight of average weight of all cereal boxes falls somewhere in that window. So that's kind of the idea. So this is always just our best guess. Why is it not letting me write? Is it frozen again? There we go. Best guess. That's all our point estimate is meant to be. If you had to guess one number, what number would you guess? 14.21, it's probably wrong, so let's add a little bit of a cushion to it. And that's what we're doing here in the second step. We're starting to figure out what that cushion should be. The critical value, in this case, is the Z or T score associated with the level of confidence. And in this case, it's going to be a T score because S and T always go together. So 8.2, we're dealing with a sample standard deviation S. S always goes with the T distribution. So the value I'm looking for is T sub alpha over 2. And we can find that by going to our table, which I have. There they are. We always just come to table A3. Take a look at table A3. I want to find the appropriate, taking a look at the picture. Let's get it all on the screen at once. Down at the bottom is really what we care about, the confidence level. And I just need to figure out which row I should be using. If I was using a normal distribution, we would use this bottom row. But in this case, we need to use a T distribution. And we need to pick the row based on, I guess I should write this down right here, based on our degrees of freedom. So this number is going to come from table A3, and the row is going to be whatever our degrees of freedom is. And our degrees of freedom is always one less than n, one less than our sample size. In this case, our sample size was 34. So one less than that is 33. I need to look in row 33. So let's go back. Let's look only in row 33. I'm going to even highlight it. Row 33. This is the row that we are allowed to look at right there. 99. Let's change my color. We'll do it this way. 99%. So I need to go up from here where they intersect. That's the value I'm looking for. So I'm looking at this value right here where those two intersected. Row 33, 99%. So 2.733 is the critical value that I need for this particular problem. 2.733. So basically what we're saying is, and we did this drawing once before, but we have a t-distribution. And this is the distribution of all the possible x bars that could live out there, all the possible average weights of the box. There's some true value mu that we're trying to predict. We don't know what it is. Hopefully it's close to 14. We found our x bar value, the specific one, to be 14.21. And so that's above average, but the question is, I don't know exactly where that our x bar that we found is 14.21, but I don't know if that's just a little bit above average or if that's way above average, because I don't really know the scale of what the numbers are on this axis here. And the reason we don't know that scale is because the scale is going to depend on how big our standard deviation, that tells us how spread out this hump is. The idea is that I don't know exactly where it falls, but I'm 99% sure it falls somewhere in this middle. That is 99% of the total area. Then I'm 99% sure it falls somewhere in there. So that's all we're going to do. We're going to say, let's just pretend we're only dealing with the middle 99%. I guess I could write that in here, 99%. Then as long as x bar falls in that middle 99%, let's pretend it falls right on the edge. In fact, let's pretend it falls right there. Then as long as I make my margin of error wide enough to at least reach out to the center, back to the center of the curve here, I will have a big enough margin of error to cover the true value, m. Right? So I don't know exactly where it falls. It technically, I'm guessing it's over here. I'm guessing it's above average, but it could not be. This could actually fall way over here at this end. My x bar could have been below the true average. Maybe these cereal boxes, even though they're labeled as containing 14 ounces, maybe they actually weigh like 14 and a half ounces, and 14.21 is actually an underestimate of the true weight. So the point is, the true value, because we don't know this number here, we can't really place where this 14.21 falls. If the true value is actually 15 ounces, then this is below average. If the true average is exactly 14 ounces, this is above average. Maybe the true average is only 13 ounces and these boxes are totally mislabeled, and this is way, way above average. We don't really know, but we're 99% sure that it falls somewhere within this amount of distance from the middle. Now we just need to figure out what that distance is. And all we've done is say that this distance right here in terms of standard deviations, that's 2.733 standard deviations wide. That's how far it takes to get out to this edge where we're cutting off the middle 99% from the remaining 1% that's out in the tails. It's 2.733 standard deviations away from the middle. Now we just need to figure out what that means in terms of actual units, in terms of ounces of cereal. So that's what this next step is. We compute the standard error. The standard error is S over the square root of N. S was the standard deviation that we observed in our calculations, 0.18 ounces. And I need to now divide that number by the square root of N. N was the 34 boxes of cereal that we had in our sample. So if we do that on the calculator, I'll get 0.18. I'll divide it by the square root of 34, hit enter, and it's tiny little number 0.031. I'll round it 3 decimals, 0.031. So it turns out one standard deviation on this curve, which would be, if this is almost 3 standard deviations, maybe this is 1, 2, and then 2.7 is right there, right at this point. 1 standard deviation, 2, 3 would be over here, so this is the 2.733. It's telling us that this distance right here, 1 standard deviation, is 0.031 ounces. And this is another 0.031. In fact, let me not label that. It's just going to make it harder to read. but this is 0.031 ounces. This is 0.031 ounces. And if I went one more standard deviation all the way over here, that would be another 0.031 ounces. But we aren't going quite 3 standard deviations. We're only going 2.733 standard deviations. So I want to figure out how many ounces is this distance, and that's going to be my margin of error M, how many ounces. And we find that over here by simply taking the product. So our M, our margin of error, is just the product of our critical value that we found in part B times the standard error that we found in part C. So step 2, right, this is always step 2, step 3, step 4, step 5, and so on. It's always just the result of step 2 times the result of step 3. This number times this number. So that is going to be 2.733 times 0.031. Let's do that on the calculator, 2.733. I could multiply it by this number with all the decimals. Doesn't matter. I'm going to just do the decimal version that's rounded. And we get 0.085 if I had to round that to 3 decimals. So that's how many ounces wide this margin of error is, 0.085-ish, less than 1/10 of an ounce. Okay, so what we're saying is, I don't know the true weight exactly. My best guess for the true weight of these boxes is 14.21, but if I add a little tiny buffer of less than 1/10 of an ounce to this, either direction, I will have an interval where I can be 99% sure that the true weight of the boxes, of all boxes of cereal, falls somewhere within that interval. And so that's what we do here. We take our X bar value and we subtract off M. We take our X bar value and we add M back to it. So the 14.21, and I'm going to subtract the 0.085. And we can do that right here, 14.21. And I'm going to subtract 0.085. And I'll get 14.125 at the low bound. And then I'll do 14.21 plus 0.085. So I can go up and, in fact, just copy this old one down, which is kind of a cool feature on the calculator. If you just go up and highlight a previous thing and hit enter, it'll just copy that down. And I'm going to just go change that minus sign to a plus sign and hit enter. And I get at the high end 14, oh, I don't know what happened there, 14.295. Okay, so I don't know exactly how much these boxes of cereal weigh. They're labeled as containing 14 ounces. That's kind of irrelevant to our question. We want to know how much is actually in there. My best guess was 14.21. That's probably wrong, but it's probably close. However, I'm 99% sure that the true weight of all those boxes is somewhere between this 14.125 and 14.295. So we're pretty zeroed in. And that's how we would spell this out. We are 99% confident that the true average weight of the cereal boxes, I can write cereal boxes, is between 14.125 and 14.295 ounces. So if I asked a follow-up question to this, like, what do we have any concerns? These boxes are labeled as containing 14 ounces. As a consumer, would you be concerned about the result that we just found? Like, as a consumer, I would want to know if it's labeled as containing 14, but it contains actually less than 14, then I'd be, frustrated. I wouldn't be getting everything I was paying for. What does this tell us? Do we have to worry about it being underweight? Well, we're 99% sure the true weight is between 14.12 and 14.29. Both of those, that whole interval is above the listed weight of 14 ounces. So I think we're good. We are pretty confident that, if anything, these boxes are ever so slightly overfilled with cereal, which wouldn't be a concern for us as a consumer buying cereal. So just kind of a way to think about what is the interpretation and then what are the consequences of that interpretation? What does this actually mean in the real world? Like, would you care? Would we care if we saw this being our interval? If our interval said, we're 99% sure it's between 13.5 and 13.7 ounces, then yeah, we would think they need to go back and relabel the boxes or start recalibrating the machines to add more cereal to each box. But as it stands, these ones look like they're giving us our money's worth in this case. Any questions on this one?
No, I'm good.
Cool. Then let's keep going. We'll look at this one. These ones are pretty easy. Hopefully at this point, we've done enough of these. If you screwed this one up way back on the first exam, you have a chance to redeem yourself because they're really straightforward. We're asked to construct a relative frequency distribution of these ages. I think we had a very similar one on previous exam review and on exam one. The important part is down here. It tells us that we're going to use 4 classes, each with a class width of 5. And we want to start with the lower class limit for the lowest class at 15. So all this is telling us is we want to make a table. And we have our classes over here. And we want a relative frequency distribution. So I need to know what the frequency is and the relative frequency. We got to have columns for both. And it tells us that we're going to have 4 classes. That just means 4 groupings. So I'm just going to do little bullet points here for each one, just placeholders. And we'll figure out what numbers go here in a minute. The first thing that we need to start this is this piece of information in the last sentence. The lower class limit for the lowest class should start at 15. So 15 is where we're starting. We're talking about ages of CNM students. 15 is the youngest we got to deal with. And the first class will go from 15 up to some mystery number that we'll figure out in a minute. The second class, though, needs to start at 20 because that's how we measure class width. And it tells us the class width should be 5. When you go from this lower class limit to the next lower class limit, that should be a jump of 5. And that means my next jump should also be 5. And my next jump should also be 5. We're basically counting by 5s for our lower limits of each class. But if that's the case, what value should the lowest class go up to? We want it to go up to, but not overlap with the 20. So we want to go to 19. And again, I'm only going to 19 because these are all whole numbers, so I can get away with a whole number here. But if these were, heights measured to an extra decimal or something, instead of just ages measured to the nearest year, I would want to include as many decimals here in these numbers as there are decimals included up in these numbers. But in this case, they're whole numbers, so I can get away with whole numbers here. So what's the next number right here? I should go up to, but not overlap with the 25. So I should go up to 24. And this one should go up to 29. And following that pattern, which is also plus 5, plus 5, plus 5, this number should be 34. And there are my 4 classes. So that's probably the trickiest part of this problem is getting these classes correct. They should all be consistently plus 5, plus 5, plus 5, and you should not overlap this. I shouldn't write a 20 here and a 20 here because then it would be ambiguous of where we should place this individual. Are they in the first class or the second class? Because 20 shows up in both lists. So don't let 20 show up in both lists. And now we just count. How many 15 to 19-year-olds are there in this list? We'll just go through it and cross them off. I see 1, 2. I only see 2. Then we'll do 20 to 24-year-olds. I see 1, 2, 3. 25 to 29-year-olds. I see 1, 2 again. And lastly, 30 to 34-year-olds, 1, 2, 3. To get the relative frequencies, we have these raw numbers, but it's different for me to tell you that there's 2 individuals between age 15 and 19 at CNM. That means something very different than saying 2 out of 10 individuals at CNM are between the ages of 15 and 19, right? 2 out of the 20,000 students would be almost none. But if it's 2 out of 10, that's 20% of the students still being teenagers. And that's a very, very different thing. And that's what the relative frequency tells us. It converts it to, instead of being absolute terms, it gives us some context. It says 2 out of how many? Well, out of how many comes from our total down here We add these up, they add up to 10. We should also be able to find that number simply by knowing that that's how many people were surveyed. There were 10 individuals surveyed. So this should always total however many people were surveyed. That ensures we didn't miss anybody as we went through the list and crossed them off. And so when it comes to the relative frequency, we don't care that there's 2 individuals. What we care about is that there's 2 out of 10. And as a decimal, that would be 0.2 or 20%. And this is 3 out of 10, which is 0.3, and so on. And so this would be 0.2 again and 0.3. I just need the decimal versions. You could write it as a fraction. You can show that work if you want. But typically, we just express these as the decimal versions of those numbers. So that's it for this first part of the problem. This is what the table looks like when we talk about a relative frequency distribution. And then in part B, we're asked to construct a histogram representing that same data, specifically the frequency tab. So I want this list of data, not the decimals. I want the whole numbers. And so in this case, I'll draw in my basic axes to draw a graph. On this side, we'll have the ages that we're interested, and on this side, we'll have the frequency, how many individuals show up. And I'm going to kind of chunk this off into 4 groups. This one will go from 15 up to 19. This next one will go from 20 to 25 or 24.999, whatever. And so just count by kind of, count the same way that we counted our lower class limits up there. Right, my first group should go from 15 all the way up to, but not quite overlapping with the 20, right? The second before they turn 20 years old. So 19 years, 364 days, 23 hours, 59 minutes type situation. We still call that person a 19-year-old. How many individuals were there? There were 2. So I just need to go up to a height of 2 for that first bar in my bar graph. The next one starts at 20 and goes up to right up to, but not overlapping with the 25. There are 3 individuals in that group, so we're going to go up to a height of 3. My next group is the 25 up to, but not including the 30-year-olds, so 25 to 29, back down to 2. And then the last group was another height of 3, so the 30 to 34-year-olds. So there's the visualization, just a quick, simple bar graph sketch. And all we're doing is copying the information here of which class are we referring to. Here's that 15 to 19-year-olds, the 20 to 24-year-olds, 25 to 29, 30 to 34, and here are the heights corresponding to the frequency of each of those groups occurring. Hopefully, quick, easy points on the real exam if you do this problem. All right. And this was, I didn't label it, this was chapter 2. If you do need a refresher on this, this was chapter 2, specifically section 2.2 is where we did these histograms and things. So you can go back and study that if you need to. Let's take a look at this one, question 17. Okay. And just let me, before we move to 17, any questions about this one here?
I don't, thank you.
Cool. Well, let's take a look at 17. All right. So again, I'm going to change this. We're not going to do both. Let's just do the p-value method because that's the approach that we've been using. So we'll stick to the p-value method. But if we use our little decision tree from the last exam, our goal is to narrow down what type of problem this is. I know it's a hypothesis test because of 2 things, if I had punctuated it correctly. First of all, there's a yes or no question. Do the proportion of men and women with gym memberships differ at a significance level of 0.05? So there's a yes or no question. And secondly, this keyword here, the significance level, that's always a term that shows up when we're talking about a hypothesis test. So I know this is a hypothesis The question is it 9.2? Is it 9.3? Is it 11.1? Is it 11.2? Which kind is it? So and the first thing to decide is how many samples we're taking. So let's read the whole question. It says, in a sample of 340 women, 132 said that they have a gym membership. In a sample of 370 men, 173 said that they have a gym membership. Do the proportions, and this is, this is another one where I did a proportion problem again. So this is another mistake. Man. All right. Well, this is an 11.3 problem, it turns out, which was one of the optional extra credit sections. So this is no good. Do I have one of these that I could come up with real quickly as an alternative? I should have vetted this. I was mostly recycling this practice test from last semester, but I totally forgot that we made those sections optional. So let's see if I have another problem. Let me just look real quickly and see if I can copy and paste something else onto here. I have a good question. Let me see. Let me see. My apologies here. Let's look. No, I want to do that one. I don't have one I can copy and paste. So let me just cross this out again. And let's just make up one here. Let me think of something I can write here. Uh, let's do like a test for the following. Okay. Number 17. A group of, I don't know, 37 individuals studied to see if maybe there's some new GLP, Wegovy, whatever type medication. Let's do a weight loss one or something like that to see if a new drug uh, helps individuals lose weight. So they are all weighed. They are weighed. Initially, then again after 3 months on the medication. The average weight loss observed is, let's say, I don't know, 13.4 pounds with a standard deviation of 11.5 pounds. Can we conclude the drug works at a significance level of 0.05? Okay, let's try this one instead. So let's just read through this again carefully, think about what it's talking about, and try to identify what type of approach is going to work for this problem. It says we've got a group of 37 individuals being studied to see if this new drug helps them lose weight. They're weighed at the beginning, and then they're weighed 3 months later after being on the medication. And the average weight loss observed is 13.4 pounds with a standard deviation of 11.5 pounds. Can we conclude the drug works at a significance level of 0.05? Okay, so the first question is this a single sample or a two sample? And we can honestly kind of think of it either way. I'm going to think of it as a two sample. We don't actually have the two samples listed out in front of us, but basically it was one group of individuals, but the samples were taken, the measurements at least, were taken at two different points in time, right? Initially and then 3 months later. So we have sort of a before and an after. We've already computed, it turns out, or been given the computation for if you took every individual, all 37, and you measured their weight before and their after, and then computed a difference. What's their before weight minus their after weight? And if the before minus the after, maybe one person was 18 pounds because they'd lost 18 pounds. Maybe another person was only 5 pounds because they lost five. Maybe somebody's was -3 because they actually gained weight. Um, we'd have this big long list of numbers. But in this case, we can just think of it as that single list. So this turns out to be probably best thought of as an 11.2 problem because it's two samples from one group. But the problem with this is that the way that we did most of our homework problems, they actually gave us the two lists, right? We had, for example, heights of 12-year-olds versus those same kids at age 14. That was one of the homework problems that showed up. And it gave us the list and we had to enter them in our calculator in order to get all the statistics. But this one, the statistics have been pre-computed for us, so it's actually easier. So we can do this one as a simple t-test on the calculator. And it's a t-test because I know it's a t-distribution because right here where it mentions the standard deviation, that standard deviation is referring to the standard deviation in the weight loss just of those 37 individuals. So it's referring just to the sample. So this is S, not sigma. So that's kind of the idea. So with this in mind, let's answer all of these parts. We should be using a t-distribution. And again, it's a t-distribution because this number right here is S. It refers only to this, to the 37 individuals in the sample. So it's the sample standard deviation. Okay, so in this case, that's our situation. Let's see if we can state the null and alternate hypothesis. So the question really is, fundamentally, right, does this new weight loss drug or medication, does it work? If the answer is no, what would I expect the average weight loss to be equal to? So we got to think about that for a minute. If this medication doesn't work, we put them on a medication that's supposed to make them lose weight. If it doesn't make them lose weight, what would we expect to see as the average weight lost? We need to keep in mind that that's what we're computing here. We have some data. We saw an average of 13.4 pounds lost. If it didn't work, I would expect to see an average of 0 pounds lost. But if it does work, if the answer is yes, to the question, does the medication help lose weight or help with weight loss? If the answer is no, then mu, the symbol we should use is actually the mu sub d. We use that in 11.2 because it's the average difference between their before and after weights. If the average difference between their before and after weights is 0, so this is the average difference in before minus after weights. If it doesn't work, then the average difference should be 0. It didn't do anything. But if it does work, then I expect to see a value greater than 0. And that would make this right-tailed. I do want to point out, we could also rephrase the question. We could ask instead, can we conclude that the drug works because that's the question. Can we conclude the drug works? What does it mean for the drug to work? It helps them lose weight. How much weight? More than nothing. Some weight. So that's why this is a 0 here. But what if instead we said, can we conclude that the drug helps them lose at least 10 pounds? Well, then I would want the number here to be 10. If the answer is no, then the average weight that I would expect them to lose might only be equal to 10 pounds. But if the answer is yes, they lost more than 10 pounds, then I would expect that average difference to be greater than 10. So in this case, it's a 0 because it just was asking, does it work at all? Does it help them lose any weight, more than 0? But if it said, can we conclude that it helps them lose more than 10 pounds, we would use the number 10 here. If lose more than 50 pounds, we'd put the number 50 here. Lose more than 1 pound, we'd put the number 1 here. So the phrasing of the question here will dictate what number goes here. And again, on the homework, there was only one question where that number wasn't 0, but I think it was the one with the heights. So if you want to go back and check that, it was, can we conclude that 14-year-old boys have grown at least 5 inches since they were 12? Like, we know they grow, right? The average height of the 14-year-old is definitely going to be higher, a bigger number than the 12-year-old, but how much bigger? Maybe we want to ask, are 14-year-olds at least 3 inches taller? Are they at least 5 inches taller? Whatever number we pick, that's the number that winds up going here as part of our null hypothesis. So it's our mu sub 0 value. Okay, with this in mind, the significance level was given in the problem for us. It was 0.05. And how do we define this? I'm going to do it again here. People that watched the last exam review all seem to get this right. If you didn't watch the last exam review, you're probably not watching this one either, but a lot of people wound up having totally different definitions or interpretations of what this meant, some of which I accepted for the most part. But basically the idea is, in terms of what this means, I know it's not asking us for that part. We don't need the critical value, but just give this significance level. What does it mean? This is the probability that we consider weird. It's our cutoff for weird. And that's ultimately what this boils down to. Like, we're asking, we're going to assume the drug doesn't work, that on average, people should lose 0 weight. But we observed that they lost 13.4 pounds. And the question is it possible that that's just a fluke, that we just got lucky? Or does it seem really unlikely for this to have happened by chance? So that is the question. How unlikely is it? So let's take a look at that. To do that, we need to compute the test statistic to try to start to place where this fits. So the test statistic is a t-score, and it's always a t-score of basically calculated using 3 things. We have our evidence, and our evidence, so in this case, is going to be the observed difference. So basically our observed difference was the average difference that we observed, d bar. We're going to subtract off the presumed average, the mu sub 0. That's what this value is here, the value from our null hypothesis. And then we divide by the standard error, which is, in this case, s sub d over the square root of n. And we can toss some parentheses around this to make it all fit together. But basically for us, that's the 13.4 minus 0. And then for the standard error, it's going to be, what were my numbers? 11.5 was my standard deviation of those differences. And I'm dividing that by the square root of whatever my sample size was. I don't know, 37. All right, so I made up these values. Let's see what that gives us for a test statistic here. So it's going to be 13.4 on top. When I subtract 0, it doesn't do anything. And I'm dividing that by 11.5 over the square root of 37. Close my parentheses, hit enter. Ooh, that is a very big test statistic. That's what you get when you make up numbers on the fly. But that is a very big test statistic. In fact, I'm not even going to use that last digit. 17.09, we'll call it. Or sorry, 7.09. What is the p-value going to be that's associated with that? It's going to be very, very tiny. How do I know? Because I want to kind of put this all together. This is our, we need to relabel it. These are D bars now. We just assumed that this drug doesn't work. If the drug doesn't work, you don't expect to see any loss, right? We assume the null hypothesis is true. If the null hypothesis is true, then I expect to see 0 weight loss. But we observed 13.4 pounds. The observed weight loss that we saw, the difference between the before and the after, was 13.4 pounds. And the question is that a little bit above average or is that way above average? And it turns out in this case, it's like off the chart over here in the table. Because the way we normally break it up is this is about 1 standard deviation, 2, 3 is right around here. We're all the way up here at 7 point something. So I picked some terrible numbers here because we were going to be off the charts to the right on this particular drawing. So it's going to be a very tiny little area. Our cutoff for what we consider weird was 5%. So, and it's right-tailed. So we're just going to cut off the most extreme, like 5%. Let me just erase some of this messiness. But we are going to come back and redo this in a minute. Come on. Ours is going to be way out there. And again, I wish I could erase this altogether. I wonder if, do I have white as a color and I can just cheat? Let me cheat and just color over this a little bit. There we go. That'll clean it up. Okay, close enough. Not quite white. Okay, so our difference that we observed was 13.4 pounds. And the test statistic, the t-score, wound up being 7.09. That's really far over here to the right. Whereas we were going to consider anything to be weird that falls in the most extreme 5%. So 0.05, here's the most extreme 5%. That would be considered weird. Anything over here would be not weird. And ours falls way to the right. So we're going to get a really tiny p-value. Let's see what it would look like on the calculator. So on the calculator to do this, I hit my stat button, go to my tests, and I'm going to do a t-test. And let me clear out some of this value. So I'm going to do stats. The observed or the presumed difference, I thought they weren't going to lose any weight, but we observed that they lost 13.4 pounds on average with a standard deviation of 11.5 pounds. And the sample size was 37, and it was right-tailed. Oops. Right-tailed. And now when I hit calculate, there's that same test statistic, 7.09, that we found a minute ago. And here's the p-value. It looks like actually a big number, 1.2, until you remember p-value is a probability. It has to be a number between 0 and 1. And the trick is to look over here to the right. You have this e minus 8. And what this means is even though this number is written as 1.2597 ... e minus 8, what it really means is I need to take that 1.25 and move the decimal place over 1, 2, 3, 4, 5, 6, 7, 8 positions. And then add a bunch of zeros. 1, 2, 3, 4, 5, 6, 7. That's the actual number. The p-value is 0.00000000125. It's a really tiny number. So this is just engineering notation, and it's used to just preserve some basically significant digits. If depending on how you're doing it, you want to see some digits. Otherwise, this whole screen would just be 0.00000, and you'd barely even be able to see what the number is, just knowing that it's tiny. So that's the idea here. It's a really tiny little area under the curve because we're off the charts to the right in this case. So I better come up with a better example before I teach this or do this practice exam next time I teach it. But for now, this is allowed. This is actually something that can happen. You can have p-values that are that small. What it means is we have really overwhelming evidence that this is in fact working. The drug seems to work. It's doing a good job. So my p-value is equal to 0 0.1, 2, 3, 4, 5, 6, 7 zeros followed by the 1, 2, 5. And that would be, again, 8 total positions, right? Hence the minus 8 from where the decimal started to where it wound up, 8 places over. So 7 zeros in the 1 make up those 8 places. Okay. Erase all that. But that's the p-value. It's very tiny. So is our result weird? Absolutely. Our result is super weird. It would be insanely weird to randomly select 37 individuals and have them lose 13.4 pounds if this drug didn't work at all. If the drug did nothing and they should have lost 0 pounds, then the odds of just by chance randomly having 37 people lose 13.4 pounds turns out to be astronomically small, which kind of makes sense. And that's what we just found. That's what these odds are. That's what the p-value is. So yes, we are going to reject the null hypothesis that the drug didn't work. Reject the idea that the drug didn't work. That's what our null hypothesis was. Reject the idea that they should have lost 0 weight because they lost a lot. We're going to reject H naught because our result is weird. How do I know it's weird? Because my p-value is 0.00000000125, which is much less than our cutoff of 5% that we were going to define weird as. And that's what this is. This is the probability that our results just happened as a fluke. What are the odds that our results were a fluke? Astronomically small. So small. So if we made an assumption, that the drug didn't work, and that assumption led to incredibly weird results, then maybe that was a crappy assumption to make. Right? If we assume the drug didn't work, and that led to insanely unlikely results of seeing people lose 13.4 pounds, maybe a better explanation is that the drug does work, and we should expect the average weight loss indeed to be a number bigger than 0. And visually what that means, again, coming back to this picture, and again, this is not something you need to do on the real exam, but can't hurt to do this here. What we're essentially saying is we just decided that, I don't want any of those red dots there. There we go. We just decided that this curve is a bad representation in all likelihood of our picture. This curve is centered at mu equals 0. Maybe this curve over here would make a lot more sense. And now this result is close to the middle, but where is this value of mu? Maybe this value of mu is 13 pounds. And maybe it makes a lot more sense to get an average of people to lose an average of 13.4 pounds if the true average amount of weight lost, if everybody were to take this medication, is like 13 pounds. So we're basically denying the idea that I don't think this curve is right. I don't think the curve centered at 0 is right. I think we have a different curve where the value of mu is definitely a number bigger than 0. And maybe then suddenly this result that was so weird on the black curve is suddenly not a weird result on the red curve. That's all we're saying right here. We're saying if I assume that this is the curve we're dealing with, where that center is 0, we got a weird result. But if I pick a different curve where mu is bigger than 0, say maybe 13, here's a different curve where maybe that result is no longer a weird result. That's all it's saying. Okay, so in plain English, we just rejected the idea that the medication didn't work. There is definitely sufficient evidence in this case. In fact, I would even go so far as to call the evidence overwhelming, but there's sufficient evidence to conclude that the alternate hypothesis is true, meaning that the answer is yes, I am expecting weight loss more than 0. There's overwhelming evidence of weight loss, that the medication works in this case. Okay, so hopefully that
So in
kind of
this
makes some
sense, it
sense.
would be okay to conclude that, I mean, to vaguely conclude that they lose weight rather than, if it was 13 pounds, we could put 13 pounds there
We don't want to
because the
put
null hypothesis is 0 or
right.
whatever.
The question we need to make sure we're answering the question that was asked. The question that was asked was, and again, not the original question, but the one that I rewrote. can we conclude that the drug works? Yes or no? That's really the question we're trying to answer. Does it help them lose
Okay.
weight? Yes or no? And the answer in this case is yes. We can conclude the drug works, it helps them lose weight. But if the question had been different, if it said, can we conclude the drug helps them lose at least 10 pounds? Then this number would have been a 10, this number would have been a 10, and this number right here would have been a 10. And it would have changed this number, which would have changed this number. We can actually see. So, like, what if that was the question? What if we changed it and said, does this drug help them lose at least 10 pounds? What would that look like? All I need to change is this value right here from 0 to 10. It was 0. Does it help them lose any weight more than 0? Now we're saying, does it help them lose more than 10 pounds? Let's calculate that. What should happen though? This number on top is getting a lot smaller. So overall, this number should get a lot smaller. So let's calculate it. It's going to be much tinier. And now our test statistic is only 1.79 instead of 7.08. And what is my p-value? 0.04. So this p-value went from astronomically small to something that's still small, but 0.04 is a lot bigger than 0.00000000125. So what would the answer be in this case? Can we conclude that the drug helps them lose at least 10 pounds at a significance level of 0.05?
We would reject the null hypothesis
Yeah,
again.
exactly. We would still be getting, it wouldn't be over here. It wouldn't be this far out in the tail, but it would be like maybe right here. It'd still be in that weird little spot because I'd only have 4% of the area in there, right? This little area. Let me pick a new color. Oh, I already did the black. Let's do whatever. We'll use a little highlighter. This little area in the tail would only be 4% of the area, right? That would be 0.04 in this case if we were doing this example. And that's definitely still smaller than 0.05, so I would know I'm still in this weird region. I'm far enough into the tail that I have a smaller area than the 5%. So I'm falling into that weird region. I'm still getting a weird result. It would be a different comparison here, but we would still reject the null hypothesis. We'd say it'd be weird to say that they only lost 10 pounds because when we saw the evidence was that they lost like 13 pounds, 13.4 pounds, to say that they only lost 10 would still be a weird result. So we
Okay.
think that they did indeed lose more than 10. It's more plausible. There's only a 4% chance that if the drug really only should have helped them lose 10, but we got lucky and just happened to get a group of people who were more susceptible to weight loss or something like that. What it's basically saying, there's only a 4% chance that that 3 extra pounds, 3.4 extra pounds, meaning the difference between the 10 pounds and the 13.4 pounds, there's only a 4% chance that that would have happened. It's just like a fluke.
Okay.
If they should have only lost 10 pounds, but they lost 13.4, yeah, that's possible. That can happen if you get lucky. But what are the odds that we just got lucky? In this case, the odds we got lucky are only 4%. So that still is less than our 5%. We would still say, yeah, this is still a weird result. So not only is there sufficient evidence to conclude that the medication works to help them lose weight, in the second question, if we'd said, does it help them lose more than 10 pounds? The answer would still be yes. There's sufficient evidence to conclude that the medication works to help them lose at least 10 pounds or more than 10 pounds, basically.
And just to be clear, typically for these problems, when you're doing the null and alternate hypothesis, that number is typically zero, but it's not always, right?
Yeah, in a lot of the examples that we did in class, it just was 0. Like it was left foot temperature versus right foot temperature, and it just said, is there a difference? Or
Okay.
it said, like, is the right foot hotter than the left foot? But it didn't say, is the right foot at least 2 degrees hotter than the left foot?
Okay.
So if it asks for a specific difference, if it just says, is there a difference or is this bigger than this, the number would be 0. But if it says something like, is the right foot at least 2 degrees hotter, or did they lose at least 10 pounds more, then that's when you would change this number to reflect that other value that's not 0.
Beautiful. Okay, thank you.
Cool. Okay. I think I need to be way more careful next time I put out this practice exam so I can come up with some better examples and not have to come up with these ones on the fly. because that also took a lot of time. But let's take a look real quickly at the multiple choice and call this a day because it's already dragging on. Okay, I'll go through these hopefully quick-ish. Let's knock them out. All right, first one is a good one. It has to do with the skew of a data set and the relationship between the mean and the median. Just looking at this graph, what can we tell about the relationship between the mean and the median? And we have three possibilities. They're about the same, the median is bigger than the mean, or the median is less than the mean, meaning the mean would be bigger. Well, what we need to remember is that this is skewed, in this case, to the right, because the tail is over here. The tail is on the right. And the little quote that was used at some point was, you can remember that these two different measures of center are each kind of affected differently when you have skewed data or when you have outliers. And the mean is the one that is more affected or more skewed by those outliers. So the mean is mean because it chases the tail. That's basically telling me is the mean might be further into the tail. The mean might be over here. The median should be less affected by the fact that this tail goes way far to the right. The mean should be always skewed in whatever direction the tail is. So the mean is skewed towards the tail. So it's skewed in the same direction as the overall skew. And so what does that mean if I located them just eyeballing, guessing that maybe they're here and here? The mean is a larger value because this number line increases as we go from left to right. The mean should be a bigger number than the median. So which one of these is the mean being a bigger number than the median? In C. So whenever you're skewed to the right, this is the example we did with like way back in the video of like imagining, I don't remember if we said Jeff Bezos or Bill Gates or somebody, if you had a billionaire suddenly join our class and ask about what is the average, net worth of an individual in our class, by adding one person that's worth $100 billion, then now our average net worth is $1 billion. But that's because that one individual skewed the mean. Whereas the median would stay about the same. Adding one super rich individual to the end of the line and asking how much is the person in the middle of the line worth, just by adding that one person at the end of the line, we aren't doing much to change who it is that's standing in the middle of the line, if that makes sense. So anyways, that's one way to think about this. Qualitative, quantitative data, a bunch of the chapter 1 stuff, different types of experiments, that's all stuff that you would expect to see here in the multiple choice. So in this case, which of these is quantitative, meaning a number? The name of a chemical sample, the mass of a chemical sample, or the color? Well, mass is the only thing that's typically measured as a number, so I should be looking for 2 only, which turns out to be C again. So we've got CC so far. Keep going. See what the others are. This is what it's looking like thus far. In a lottery drawing, 6 balls are randomly drawn from separate spinning cages. What kind of sample is being used? This is like the case, dictionary definition of a simple random sample, pulling balls as randomly as possible. So this is a simple random sample. So the answer would be B. Right? It's truly a random process where you're just as likely to draw any one ball as any other ball. Every outcome is equally likely to occur. Number 4, we saw this on a previous exam. I think we had this on, no, I guess we didn't because we just introduced this concept. I used to like to put this one on other exams, but this is a really good one having to do with correlation. Which one of these has a larger correlation coefficient and why? And so correlation coefficient, we talked about it as being basically the way that we measure how obvious the trend in data is. So that's what you really want to think about it. The correlation coefficient, the larger it is, the closer to 1. 0 means no correlation. The data would look totally random. But the closer you get to 1, it should mean that the trend line is becoming really, really clear. So imagining that we have 2 little trend lines, which of these 2 trend lines fits the dots better? B, right? The line almost covers the dots. The dots are basically on the line, whereas this one, they're still kind of spread out a little bit. And so that's the distinction we're looking for. B has a larger correlation coefficient because the spread between those points is smaller. They all fall almost right on the line. Where here you can see the dots kind of still spread out. You can still see the trend line, but the dots are kind of spread out a little bit. Steepness doesn't matter other than determining whether we're going uphill or downhill. That's the difference between positive and negative correlation. So the steepness only determines positive versus negative. That's all we care about in that regard. So the answer to this one is D. Here's some chapter 5 stuff. We've got to remember our general addition rule that says the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. And so we just need to plug in the values here. It gives us all three of those values on the right. We need to figure out the one on the left. So the one that we're looking for, if I can write correctly, A or B is going to be equal to probability of A, which is 0.21, plus the probability of B, 0.37, minus the probability of A and B, 0.12. And so if we do those on the calculator here real quickly, we've got 0.2, come on, turn on, 0.21 plus 0.37 minus 0.12. 0.46. The answer is B. So go back and just make sure that you remember this. Remember the definition of like mutually exclusive means there's no overlap. So the probability of A and B would be 0 in that case. Remember that I gave you these three quantities in this problem and asked you for this one, but I could give you this one and this one and this one and ask you for this one. For example, I could say, here's probability of A or B, here's probability of A, here's probability of B. Are they mutually exclusive? And you'd have to solve for this one and see if it's 0 or not. Okay, 6 and 7, these are very similar to questions that we were asked on the last exam. I like these questions. You're probably going to see something similar to these because I think they do a really good job of just testing the concept between confidence intervals, like what should help a confidence interval. Number 6 says a 95% confidence interval for a sample of size n equals 48 has a margin of error of m equals 5.74. If all else stays the same, but we instead compute a 99% confidence interval, what would happen to the margin of error? So if our confidence goes up, right, the analogy we used was like trying to hit a target. If I want to go from being 95% sure I can hit the target to being 99% sure I can hit the target, if I want to be more sure I can hit the target, what do I need to do to the target? How do I need to make it bigger or smaller? Well, I need to make it easier to hit because I want to be more confident that I can hit it. That means making it bigger. And that's exactly what we need to do. The other way to tell is because this is basically looking at the formula for the margin of error in one of those confidence intervals. This is the number being affected by the confidence level. And if I want to go from 95 to 99, just find that table. Where did I put that table? It's down here. Scrolling the wrong way. Here we go. If I want to go from 95 to 99, the number goes from 1.96 up to 2.57. The number gets bigger. And that's exactly what we're seeing here. If that number gets bigger, come on. If this number gets bigger and everything else stays the same, then this overall number should get bigger. So there's a mathy way to look at it and also just the big picture concept of trying to hit a target. Same setup. In this case, we have a 95% confidence interval, sample of size n equals 48, margin of error of m equals 5.74. If all else stays the same, but we instead are able to take additional samples so that n goes up to 60, what will happen to the margin of error? And the question here is just big picture. Is having a bigger sample a good thing or a bad thing? Generally speaking, bigger samples are better. The bigger the sample we take, the better results we're going to be getting, right? You can't just sample one individual and say like, oh, I want to find the average height of, a person in New Mexico or something. If you just pick one person, that's not going to give you a very good estimate. It's very possible that you'll accidentally happen to pick a person that's either abnormally tall or abnormally short, and your result will be way off. But if you instead take a sample of 10 people Well, then you're getting something better. 100 would be better than that. 1,000 would be better than that. So the bigger your sample is, the more zeroed in on the correct value you should expect to be. And that's what's going on here. If I increase my sample size, I should expect to be more zeroed in on the value I'm trying to find. What does it mean to be zeroed in? It means that my margin of error should go from an interval that looks like this to an interval that looks like this. This one is more zeroed in. And that's what happens when we get a larger sample size. So a larger sample size, my margin of error should decrease. I should be more zeroed in on the value I'm looking for. And that's what's going on here. Again, mathematically, what's happening is if I increase n, it's sitting in the denominator. The denominator gets bigger, the overall number gets smaller. And that's what's happening in this case. 8. By visiting homes door to door, a politician surveys all the households in 12 randomly selected neighborhoods to see whether residents support his candidacy. Identify the type of sample that's being used. That is a cluster sample. Cluster samples are where we break up the whole population, in this case, whatever all the citizens or voters in the city. We break it up into groups, in this case, neighborhoods, and then we just randomly pick some of those groups and survey all the individuals that fall into some of those groups. So the random sampling occurs at sort of a high level in terms of which groups we're even going to look at. This is sometimes easy to confuse with a stratified sample where you also take the population and break it into groups. But in a stratified sample, you don't look at only some of the groups, you look at every group and you do your random sampling within each of those groups individually to make sure that you get appropriate representation from each of those groups. So cluster samples occur at a higher level. The random sampling occurs in terms of even picking which groups we're going to consider, in this case, the neighborhoods. So that's a cluster sample. Let's do 10 because it's easier, and then I'll come back and do 9 because it involves that table that we got to draw real quick. But number 10, rolling a 6-sided die, the results range from 1 to 6. Characterize the nature of the roll outcome. Well, 1 to 6, they're numbers, so they're definitely quantitative. We can rule off the qualitative ones right from the get-go. I did a poor job of crossing that out. Come on, pencil. So it's definitely one of those two, and it's discrete in this case because you cannot roll a 2.37964 whatever. You can roll a 1 or a 2 or a 3 or a 4 or a 5 or 6, but nothing in between. Discrete means there are gaps between the possible outcomes. So quantitative and discrete. Number 9, this is the last one that we've got. I'll just try to do that table real quickly. Hopefully I draw it the same way I drew it last time. I try to be consistent in the way that I draw it. We have the reality of the situation on this hand, that H naught is either actually true or H naught is actually false. This is kind of the guilt versus not guilt. And we have reject it versus not reject it. This is the decision that's made. And if it's false and you reject it, that is the correct decision. If it is true and you don't reject it, that is the correct decision. So those are the two correct decisions we can make. These are the two different types of errors. If it's false, but we don't reject it, this, you can think of this as the person's actually guilty. They murdered the person, but we let them off. That's a type 2 error. Type 2 errors basically being too lenient. Type 2. Type 1 is they were actually innocent, but we rejected the idea of them being innocent and convicted them. So that's a type 1 error. So this is our table. We just need to figure out which one applies in this case. So in this case, we have a test of mu being equal to 56 versus mu being less than 56 is performed using a significance level of 0.05. The p-value is 0.174. If the true value of mu is 56, does the conclusion result in a type 1 error, type 2 error, or a correct decision? Well, right here we have that the true value of mu is indeed 56, so that's important. So because the true value of mu is 56, and the null hypothesis was that mu is equal to 56, which of these cases do we have? Is the null hypothesis true or false? Well, it turned out to actually be 56, which matches the null hypothesis, so the null hypothesis turned out to be true. So we're somewhere in this column. We got one of these. We can rule out the other column. Next, we've got to decide whether we rejected the null hypothesis or not, and that comes from comparing our p-value to our significance level. Did we reject H naught, yes or no? Well, in this case, our p-value, and we want to compare it to alpha, the p-value is 0.174. The value of alpha is 0.05. Would we reject the null hypothesis? No, because the p-value is greater than the significance level. So the answer is no. We did not reject the null hypothesis in this case. If we did not reject the null hypothesis, well, this is going to make an ugly color. It's not too bad. We did not reject it. So this was our situation, meaning, oops, we have, come on, pencil, a correct decision. That's the one that we wound up in. So we did a similar one on the last exam and the last practice exam. You can go through that again if you want to see another example of something like this. Might have even been the same problem. I can't remember. Definitely similar. Okay, well, that went way longer than I was hoping. Before I log this off and call it a day, does anybody have any other questions about this?
No, I don't. Thank you so much.
Of course. Sorry it went so long. Hopefully it's not too bad to go sit back and go through it. But good luck on the real exam. Again, just a reminder, you can take it starting tomorrow if you want to get it out of the way, all the way through Saturday. But I do need you to finish them by Saturday because I have to grade them on Sunday because grades are due early next week. So if an emergency comes up and there's an absolute like no way for you to take it Saturday, you have to take it Sunday. I maybe just email me, but hopefully that's not the case for most people. So otherwise, it was a great semester. I hope all of you feel like you learned something and at least got through math, maybe feeling like you don't hate it or aren't quite as scared of it as you used to be. And if you already liked math to begin with, then maybe this gave you kind of a new some new insights. Statistics is so different from other math, can be kind of cool. Not everybody thinks so, but I do. So, anyways, have a great break, everybody.
Thanks again.
Of course, take care.
You too.